The radar dish completed another sweep. No human eyes watched the storm approaching. The National Weather Service Storm Prediction Center hummed with electronic vigilance at 2:47 a.m. Its array of sophisticated monitoring systems maintaining their eternal watch over atmospheric conditions across 3,000 miles of North American weather patterns. Outside, the October night was deceptively calm, but the radar screens inside painted a different story. A massive storm system was building strength over the Gulf of Mexico, its spiral arms reaching toward the coastline like the fingers of some meteorological giant. The main radar installation, a 40-foot dish mounted on a tower that rose 200 feet above the Texas plains, rotated with mechanical precision. Every 6 minutes, it completed a full 360-degree sweep, sending pulses of electromagnetic energy into the atmosphere and listening for the echoes that would reveal the hidden architecture of weather systems invisible to human eyes. The radar dish knew nothing of human concerns about property damage or evacuation plans. It simply measured, with scientific objectivity, the water droplets and ice crystals that danced in the sky above. But this radar system had been tracking storms much longer than any human meteorologist had been alive, watching weather patterns that connected today's atmospheric conditions to climate cycles spanning decades. The Doppler radar system interpreted the velocity of precipitation particles, painting velocity couplets on screens that revealed the rotation signatures of developing tornadoes. Red pixels indicated motion toward the radar, green pixels showed motion away, and the tight spirals where red met green marked the atmospheric violence that could spawn the most destructive weather phenomena on Earth. The computer algorithms processed this velocity data with mathematical precision, calculating wind shear and rotation strength with accuracy that exceeded human perception. Atmospheric pressure sensors throughout the facility detected microscopic changes in barometric pressure, variations so subtle that human senses could never detect them, yet significant enough to indicate major weather pattern shifts hundreds of miles away. These sensors fed data to computer models that projected pressure gradients and storm track predictions, their electronic minds processing atmospheric physics equations that describe the behavior of fluid dynamics in three-dimensional space. The satellite communication array maintained constant contact with weather satellites positioned 22,000 miles above the Earth, receiving continuous streams of infrared and visible light imagery that revealed cloud formations across entire continents. These satellite images updated every 15 minutes, creating time-lapse movies of storm development that compressed hours of atmospheric evolution into minutes of visual data. Now imagine standing in that darkened control room, surrounded by glowing screens that display the secret life of the atmosphere, watching storms that exist as mathematical models before they become physical reality. Lightning detection networks spread across the continent fed real-time data about electrical activity within storm systems, each lightning strike registered as a precise geographic coordinate and electrical intensity measurement. These lightning data created electromagnetic fingerprints of storm cells, revealing their internal structure and energy levels through the analysis of electrical discharge patterns that accompany different types of severe weather. Atmospheric temperature monitoring systems measured atmospheric conditions at multiple altitudes, using radio signals to probe temperature variations from ground level to the stratosphere. These temperature profiles revealed the atmospheric instability that fueled severe weather development, identifying layers of warm and cold air whose boundaries became the battlegrounds where storms gathered their destructive energy. Wind profiler systems sent radio pulses skyward to measure wind speed and direction at various altitudes, creating three-dimensional maps of atmospheric motion that revealed the invisible rivers of air that guided storm movement. These wind measurements allowed prediction computers to calculate storm tracks with precision that extended accurate forecasts days into the future. Listen to the whisper of electromagnetic pulses probing the atmosphere, reading the invisible signatures of weather systems that could affect millions of lives in the communities that sleep peacefully below. The Storm Prediction Center's supercomputers processed weather data from thousands of observation stations, creating numerical weather models that simulated atmospheric behavior using equations derived from fluid dynamics and thermodynamics. These computer models ran continuously, calculating multiple scenarios for storm development and tracking, providing meteorologists with probabilistic forecasts that quantified uncertainty in weather prediction. Automated weather stations scattered across the region transmitted surface observations every minute, reporting temperature, humidity, wind speed, wind direction, and barometric pressure to central processing systems that integrated surface data with upper-level atmospheric observations. These ground-based measurements provided the foundation data that anchored computer models to actual atmospheric conditions. The emergency alert system maintained constant readiness to broadcast severe weather warnings to television stations, radio networks, and wireless emergency alert systems throughout the region. This system could disseminate life-saving information to millions of people within minutes of severe weather detection, coordinating with local emergency management agencies to ensure that warnings reached populations at risk. Emergency systems stand ready to wake sleeping communities with warnings that could save lives, their electronic vigilance protecting people who trust that someone is always watching the weather while they sleep. The radar data processing computers analyze reflectivity patterns to identify precipitation types, distinguishing between rain, snow, sleet, and hail based on the electromagnetic signatures of different hydrometeor species. These computers could detect hailstones as small as pea-sized or as large as softballs, providing advance warning of agricultural damage and automotive hazards from severe thunderstorms. The Storm Prediction Center maintained detailed databases of historical weather patterns, comparing current atmospheric conditions to thousands of previous weather events to identify analog situations that provided insights into likely storm behavior. These historical comparisons allowed forecasters to recognize patterns that preceded significant weather events, improving the accuracy of severe weather predictions. Atmospheric sounding systems measured vertical temperature and moisture profiles by tracking weather balloons equipped with radiosondes, instruments that transmitted data about atmospheric conditions as they ascended through the troposphere and into the stratosphere. These soundings provided critical data about atmospheric stability and the energy available for thunderstorm development. Weather balloons carry electronic messengers into the sky, measuring atmospheric conditions that will determine whether tonight remains peaceful or becomes a night of severe weather that tests emergency response systems. Mesoscale weather models focused on high-resolution atmospheric simulation over smaller geographic areas, providing detailed forecasts for regions where terrain features influenced local weather patterns. These specialized models incorporated topographic effects, land use variations, and urban heat island influences that affected storm development and intensity in specific locations. The wind shear detection system measured differences in wind speed and direction at various altitudes, identifying atmospheric conditions that could either suppress or enhance thunderstorm development. Strong wind shear could tear apart developing storms, while moderate shear could organize storms into supercells capable of producing tornadoes and damaging hail. Communication systems maintained contact with National Weather Service forecast offices throughout the region, coordinating storm spotters and emergency managers who would implement protective actions based on weather center predictions. These communication networks ensured that meteorological expertise
reached decision-makers who could order evacuations or activate emergency shelters. Communication networks carry meteorological intelligence to emergency managers who make life and death decisions based on atmospheric measurements that reveal nature's intentions before nature acts. The Storm Prediction Center's display systems presented weather data in formats that revealed patterns invisible to casual observation, using color coding and animation to show atmospheric motion, temperature variations, and precipitation intensity. These visualization systems transformed abstract meteorological data into intuitive graphics that communicated complex atmospheric information quickly and accurately. Severe weather databases maintained records of tornado paths, hail reports, wind damage, and flood events, creating climatological references that helped forecasters understand regional weather patterns and seasonal variations in severe weather frequency. These databases provided statistical context for evaluating current weather threats against historical precedent. Automated data quality control systems verified the accuracy of weather observations from thousands of sensors, identifying instrument malfunctions and data transmission errors that could compromise forecast accuracy. These quality control algorithms ensured that weather predictions rest on foundations of verified atmospheric measurements, protecting forecast accuracy from instrument failures and transmission errors that could compromise public safety warnings. The Radar Network Coordination System integrated data from multiple radar sites to create composite images showing precipitation patterns across multi-state regions. This radar mosaic provided comprehensive storm surveillance that eliminated gaps between individual radar coverage areas, ensuring that no significant weather systems escaped detection. Storm-scale modeling systems simulated the internal structure of individual thunderstorms, calculating updraft strength, downdraft velocity, and rotation potential with resolution that approached the scale of tornado-producing processes. These high-resolution models provided insights into storm behavior that guided decisions about tornado warning issuance. Climate monitoring systems tracked long-term atmospheric patterns that influenced seasonal weather variations, identifying climate oscillations like El Niño and La Niña that affected storm frequency and intensity over periods of months to years. These climate indicators helped forecasters understand the broader atmospheric context that influenced regional weather patterns. Climate systems revealed the long-term atmospheric rhythms that determine whether storm seasons will be active or quiet, providing seasonal context for understanding current weather patterns. The Emergency Alert System maintained protocols for disseminating different types of weather warnings, from routine advisories to life-threatening emergency warnings that triggered immediate protective actions. The system could target specific geographic areas with precision that minimized unnecessary alarm while ensuring that populations at risk received timely warnings. Meteorological education systems preserved training materials and reference guides that helped forecasters interpret complex atmospheric data and recognize subtle signs of severe weather development. These educational resources ensured continuity of forecasting expertise and supported ongoing professional development in weather prediction techniques. All these systems operated with coordinated precision throughout the night hours. Their electronic consciousness focused on atmospheric surveillance that protected sleeping communities from weather hazards they would never see approaching. The systems felt no anxiety about the storms they tracked. experienced no urgency about the warnings they prepared to issue, knew only the satisfaction of perfect meteorological vigilance. The Storm Prediction Center maintains its weather watch with electronic patience that never tires, never becomes complacent, never stops measuring the atmospheric conditions that determine whether communities awake to sunshine or storm damage. The radar systems continued their methodical sweeps, painting electromagnetic portraits of atmospheric motion that revealed the invisible architecture of weather systems. Each radar pulse contributed to a growing understanding of storm behavior that protected millions of people who slept peacefully, trusting that meteorological technology would provide advance warning of any weather that could threaten their safety. And you, listening to the electronic symphony of these weather monitoring systems, can rest in the knowledge that atmospheric surveillance never sleeps, never takes breaks, never stops watching the sky for signs of weather that could affect human life and property. The systems that surround sleeping communities represent decades of meteorological engineering, each component refined through years of severe weather events to achieve reliability that protects lives through accurate and timely weather warnings. Sleep now, knowing that the atmosphere is being watched by electronic guardians that can see storms forming before they become visible, measure winds before they become destructive, detect rotation before it becomes tornadic. The Storm Prediction Center's gentle electronic meditation continues as consciousness fades, the steady rhythm of radar sweeps and data processing guiding you into peaceful sleep. In the morning, you will awaken to accurate weather forecasts based on overnight atmospheric monitoring that never paused, never rested, carried safely through the night by meteorological systems that measure the sky's intentions while you dream peacefully beneath whatever weather tomorrow may bring. Sweet dreams, protected by the vigilant watch of weather radar systems that scan the horizon for atmospheric dangers, measuring storm potential in electronic silence that ensures your morning will bring weather warnings if warnings are needed, or peaceful skies if peace is what the atmosphere holds in store.
Protected by the vigilant watch of weather radar systems that scan the horizon for atmospheric dangers, measuring storm potential in electronic silence that ensures your morning will bring weather warnings if warnings are needed, or peaceful skies if peace is what the atmosphere holds in store. But the Storm Prediction Center's mission extended far beyond simple weather observation. It had become the electronic nervous system for an entire continent's atmospheric awareness. The storm tracking algorithms had evolved into sophisticated pattern recognition systems that could identify atmospheric signatures hours before human meteorologists would detect them. These algorithms analyzed millions of data points from surface observations, upper air measurements, and satellite imagery to recognize the subtle atmospheric fingerprints that preceded severe weather development. They had learned to read the sky's intentions through mathematical analysis of pressure gradients, temperature differentials, and moisture transport patterns. Advanced numerical weather prediction models ran continuously on supercomputers that processed atmospheric physics equations millions of times faster than human calculation could achieve. These models simulated the behavior of air molecules across thousands of cubic miles of atmosphere, calculating how pressure systems would move, how temperature patterns would evolve, and how moisture would organize into precipitation systems that could affect millions of people. The hurricane tracking systems maintained specialized focus on tropical cyclone development and movement, using satellite imagery to identify tropical disturbances before they achieved organized circulation. These systems tracked the eye wall structure, measured central pressure drops, and calculated storm surge potential for coastal areas that lay in the projected path of approaching hurricanes. The tracking computers understood that hurricanes exist as mathematical equations describing the conversion of thermal energy into rotational motion. Storm systems understood through the pure language of atmospheric physics. Flood prediction systems integrated rainfall measurements with watershed models that calculated runoff patterns and river flow rates throughout drainage basins spanning multiple states. These hydrological models could predict flash flooding hours before dangerous water levels developed, providing advance warning for communities located in flood-prone valleys and urban areas where storm drainage systems could become overwhelmed by intense precipitation. The tornado detection algorithms analyzed radar velocity data to identify mesocyclonic rotation within supercell thunderstorms, calculating vorticity values and shear parameters that indicated tornado development potential. These algorithms could detect tornado formation at stages when the rotation remained invisible to human observation, providing precious minutes of advance warning for communities in the path of developing tornadoes. Severe weather climatology databases maintain statistical records of atmospheric conditions that had produced significant weather events throughout meteorological history. These databases allowed current atmospheric patterns to be compared against historical analogs, providing probabilistic guidance for forecasting rare but high-impact weather events that occurred infrequently but caused extensive damage when they developed. Historical weather patterns live in electronic memory banks that can instantly recall atmospheric conditions from decades past, comparing today's weather setup to every significant storm that preceded it in meteorological history. The atmospheric chemistry monitoring systems tracked pollution transport and air quality conditions that affected public health warnings associated with weather patterns. These systems could predict when stagnant atmospheric conditions would concentrate air pollutants to unhealthy levels, or when strong wind patterns would disperse atmospheric contamination and improve air quality across metropolitan areas. Lightning mapping networks used multiple sensor stations to triangulate the precise geographic location of every lightning strike across the continent, creating real-time maps of electrical activity that revealed the internal structure and intensity of thunderstorm systems. The lightning data provided insights into storm evolution that complemented radar observations with electromagnetic measurements of storm electrical energy. The Storm Prediction Center's communication protocols maintained standardized procedures for coordinating weather information among federal, state, and local emergency management agencies. These protocols ensured that meteorological expertise reached decision-makers who implemented protective actions, from school closures to evacuation orders, based on weather predictions that originated in the electronic surveillance systems. Communication protocols transform atmospheric measurements into human actions, converting radar data and computer model output into decisions that protect lives and property from weather hazards that most people never see developing. Aviation weather systems provided specialized forecasts for aircraft operations, calculating wind shear conditions, turbulence potential, and visibility restrictions that affected flight safety across thousands of airports and flight routes. These aviation systems understood that aircraft operations required meteorological precision measured in minutes and miles rather than hours and regions. Marine weather systems focused on oceanic and coastal atmospheric conditions that affected shipping, fishing, and recreational boating activities. These systems tracked wind patterns over water surfaces,
calculated wave height development, and predicted fog formation in coastal regions where marine and terrestrial atmospheric conditions interacted in complex patterns. Fire weather monitoring systems identified atmospheric conditions that increased wildfire risk, measuring humidity levels, wind patterns, and atmospheric stability factors that determined fire behavior and suppression effectiveness. These systems could predict when atmospheric conditions would support rapid fire spread or when weather patterns would assist firefighting operations. Specialized weather systems serve every human activity that depends on atmospheric conditions, from agriculture to aviation, from marine operations to wildfire management, each requiring meteorological expertise tailored to specific atmospheric hazards. The Storm Prediction Center's quality assurance systems continuously verified the accuracy of weather forecasts by comparing predicted atmospheric conditions to actual observed weather events. These verification systems provided feedback that improved forecast accuracy and identified systematic biases in weather prediction models that could be corrected through algorithm adjustments.
International weather data exchange systems maintained coordination with meteorological services worldwide, ensuring that atmospheric observations from one continent contributed to weather understanding on other continents. Weather systems recognized no political boundaries, and global atmospheric monitoring required international coordination to track storm systems that moved across oceans and affected multiple nations. The emergency backup systems prepared for the possibility that the technology protecting communities from severe weather might itself become a victim of the severe weather it monitors, ensuring that atmospheric surveillance continues even during the storms that test all systems. All these interconnected systems worked together throughout the night hours, their electronic consciousness focused entirely on atmospheric surveillance that protected sleeping populations from weather hazards they would never directly observe developing. The systems felt no concern about the human consequences of the weather they tracked, experienced no emotional involvement with the communities they protected, knew only the mathematical precision of atmospheric measurement and the electronic satisfaction of perfect meteorological function. The Storm Prediction Center had achieved the ultimate expression of weather monitoring technology, systems that could see atmospheric dangers before they became visible, measure storm intensity before it became destructive, predict weather impacts before they occurred. Every sensor, every algorithm, every communication system had evolved through decades of severe weather events to achieve reliability that saved lives through accurate and timely weather prediction. In the electronic depths of the Storm Prediction Center, weather achieves its purest technological expression. Perfect atmospheric surveillance serving human safety through mathematical precision that converts atmospheric chaos into predictable patterns. The weather monitoring systems represented humanity's most sophisticated attempt to understand and predict the behavior of atmospheric systems that operated according to physical laws, but displayed behavior that approached the complexity of living organisms. They had learned to read the atmosphere's intentions through electronic senses that exceeded human perception and mathematical analysis that surpassed human calculation. And you, resting under the protection of these atmospheric guardians, can sleep peacefully knowing that weather surveillance technology maintains constant vigilance over the sky above your community. The systems that monitor atmospheric conditions represent generations of meteorological engineering, each component refined through countless severe weather events to achieve the reliability that protects human life through accurate weather prediction. Sleep now, cradled in the electronic embrace of weather monitoring systems that never rest, never stop scanning the atmospheric conditions that determine whether you wake to gentle sunshine or need advance warning of weather that could affect your safety. The Storm Prediction Center's gentle electronic hymn continues as consciousness fades, the steady rhythm of radar sweeps and atmospheric measurements guiding you into peaceful sleep. In the morning, whatever weather awaits will have been measured, analyzed, and predicted by systems that worked throughout the night to ensure that atmospheric surprises would not surprise the communities they serve. Sweet dreams under the watchful protection of the weather guardians in the electronic sanctuary where atmospheric science serves human safety through mathematical precision that reads tomorrow's weather in tonight's atmospheric data.